Okay, so today we are very happy to have Asfaq Hossain from IISER Bhopal. So Asfaq completed his Ph.D. under the supervision of Professor Debashish Goswami at the Indian Statistical Institute, Kolkata, December 2022. Research primarily focused on quantum symmetry of finite spaces and their application across various areas of mathematics. He's also exploring other areas of noncommutative mathematics as well. Currently, he is a postdoctoral fellow at Indian Statistical Institute and Research, IISER Bhopal. The talk he will be presenting based on his doctoral research. We will talk about quantum symmetry in multigraphs. Asfaq, please start.
Yeah, okay. Thank you for that lovely introduction. And I would like to thank the organizers for inviting me for this talk. And today we'll talk about quantum symmetry in finite multigraphs. And this is a joint work with Professor Debashish Goswami. And it is also a major portion of my thesis. So we will start with a small introduction about what this term quantum symmetry means to me. And yeah, so for a compact Hausdorff space X, that is a compact Hausdorff topological space X, the function algebra, we know that the function algebra Cx, that is the set of all complex valued continuous function on X, is a commutative unital sister algebra. And conversely, as the famous Gelfand-Neymark theorem states that for any commutative unital sister algebra A, there actually exists a compact Hausdorff space X such that A is isometrically isomorphic to Cx. So in non-commutative mathematics, instead of studying the properties of X, we study somewhat equivalent properties on its function algebra A. So, and by doing that, the underlying commutativity assumption of the algebra becomes kind of redundant. And in that regard, a quantum space is basically a non-commutative sister algebra. So a quantum space is just an algebra. There is no space there. Because if there is a space there, then the function algebra is inherently commutative. So there cannot be an underlying space. A compact quantum group, which was the analytic setting was first introduced by Voronowicz in his seminal work, Compact Matrix Pseudogroups, and we will work in this Voronowicz framework. And a compact quantum group is a unital sister algebra with a coproduct map, delta, which is a sister algebra homomorphism from A to A tensor A, satisfying the following properties. By the way, in this talk, all the sister algebras will be unital, and all the tensor products will be minimal tensor product of sister algebras, unless explicitly mentioned otherwise. So the first property that this coproduct map has to satisfy is called something called coassociativity, which basically says that the identity tensor delta composed with delta equal to delta tensor identity composed with delta. And we'll see what this thing means. And the second property is something called biasimplifiability, which says that each of the linear spans of these things, delta A into A tensor 1 and delta A into 1 tensor 1. So basically, these are linear subspaces of the algebra A tensor A, and they have to be norm dense in A tensor A. So if our, let's say our algebra A is commutative, then by Gelfand-Neymark theorem, we actually have a compact Hausdorff space G such that A is isometrically isomorphic to CG. And this coproduct map actually induces a multiplication map inside that set G. And this coassociativity property will ensure that the multiplication is actually associative multiplication, which is a required property for group multiplication. And this density properties, this biasimplifiability property, makes sure that each element in the group has a multiplicative inverse, which is also another required property for something to be a group. So in that way, a compact quantum group is basically a non-commutative generalization of a compact topological group. And as groups can act on a space through capturing its symmetry. So when a group acts on a space, it captures its symmetry. Similarly, one can define coactions of quantum groups on spaces. Maybe I should say the function algebra of the spaces. And these coactions actually captures the quantum symmetries of the space or the generalized symmetries of the space. So this whole philosophy, we will see the application of this whole philosophy in the context of finite structures. And in that regard, we introduced the notion of the quantum permutation group. And sorry, not we introduced, actually, it was introduced by Wang in his seminal work in 1998, Quantum Symmetry of Finite Spaces. I just describe it here because this is the prerequisite of my work. And we start with the finite set Xn, which is an n set, that is a set consisting of n elements. A coaction of a compact quantum group. So CQG is a small abbreviation for the compact quantum group. So a coaction of a CQG 8 delta, where A is the algebra and delta is the coproduct map on the algebra, on Xn is a hystoalgebra homomorphism alpha, which is again a map from Cxn to Cxn tensor A, such that the following conditions are satisfied. The first one says that the alpha tensor identity composed with alpha equal to identity tensor the coproduct map delta composed with alpha, and the second one says is some sort of density properties that we had in that definition of coproduct map, that the linear span of this thing is non-dense in Xn tensor A. So what happens if our CQG is actually a classical compact group? And the first condition basically tells that the action of a group on this finite set is compatible with the multiplication map in that group. And this density property actually ensures that the identity element of the group acts on Xn by an identity map on Xn. So this is how this notion of coaction on a finite set is basically a non-commutative generalization of group action, compact group action on a finite set.
Can you ask something? Can you hear me?
What? Pardon?
Yeah. I have a question. If you want to generalize the action on the finite set of the group, why you don't define an action of the compact quantum group? Why do you need coaction instead of action?
Okay. So this is basically a kind of a difference of philosophy. I mean, because when we write action in the context of a group, so this is basically a map from G cross X to X. And to get the coaction, we need to dualize this map. That is, we need to see a map from alpha. So given a group action, we need to dualize this map to get a map from Cx to Cx tensor Cg. Since we are to justify this dualizing process, we are using the term coaction because the arrows are getting reversed. Even when we talk about this category of actions and coactions, every arrow a subgroup is a subset of a group, but in the case of a quantum group, we will get a surjective homomorphism from the function algebra to the algebra of the subgroup. So arrows are getting reversed. That's why we're using the quota.
Okay, thank you.
Okay, so moving on. These two properties, actually, these properties of coaction can be, at least in the context of a finite set, it can be described in purely algebraic way. So for that thing, we describe the notion of the transformation matrix of a linear map. So any linear map alpha, which is a map from Cxn to Cxn tensor A, and here it doesn't have to be a CQG, and it can be written by this finite sum formula, where this chi i's are basically characteristic functions inside Cxn, and that is that chi I evaluated at I prime equal to 1 if I equal to I prime, and otherwise it is 0. And these qij's are basically elements of A, and this matrix qij equal to 1 to n, it is an n cross n A valued matrix, and it actually determines how the map alpha is. So, and this is called the transformation matrix of alpha, and one can show that alpha is a coaction, that if alpha is a hystoalgebra homomorphism from Cxn to Cxn tensor A satisfying those properties, if and only if the coefficients of the transformation matrix Qij, ij equal to 1 to n, satisfy the following. So the first thing is that all the entries of the matrix Qij, they have to be projections, that is Qij square equal to Qij equal to Qij star for all ij equal to 1 to n. And the second is that the sum of each row and sum of each column of this a-valued matrix Qij, I equal to 1 to n, is also unity. And these relations, the above set of relations are called quantum permutation relations, and they are actually introduced by Wang in his paper. And the universal object in the category of all the CQGs, you can use the word coacting or acting, I mean, depending on the context. So all the universal object in the category of all the CQGs coacting on CXN is basically the universal sister algebra generated by the coefficients of this matrix satisfying quantum permutation relations. So in a way, like in classical scenario, the classical permutation group Sn basically is the largest group that can act on a finite set. And exactly same kind of thing that we are saying, same kind of philosophy we are propagating here in the quantum setting, where the universal object in the category of all CQG is coacting on Cxn, that is the largest quantum group that can coact on this, maybe act on this set Xn, is basically the universal sister algebra generated by these symbols satisfying quantum permutation relations. And one can actually show that there exists a matrix core product structure on this universal sister algebra, making this algebra a genuine compact quantum group. And this is called the quantum permutation group Sn plus.
We can ask you something. So these Qij, they are not scalar. They are what?
No, they are not scalars. They are not scalars. They are algebra valued. A is basically sister algebra valued. Yeah.
Okay. It's a matrix of sister algebra.
Yeah. So, like, if our sister algebra is commutative, then one can show that it is a basically quotient of C of Sn, the set of continuous functions on the classical permutation group Sn. But Sn is discrete, so it basically means that there is no continuous topology inside Sn. So it's just a subset of set of all functions on Sn. So the next question will be that okay, how big is this Sn plus? I mean, I need to, like, if I am like terming something as generalized symmetry, I need to at least produce some something that is not generated by classical actions. So in that context, one can see that for n equal to 1, 2, 3, the quantum permutation group Sn plus actually becomes commutative and reduces to the classical group Csn. And that is that for n equal to 1, 2, 3, we don't have anything much. But for n greater than equal to 4, one can show that Sn plus is infinite dimensional and truly non-commutative. And to see this phenomena, we consider a coaction on this force set implemented by this following transformation matrix, where basically P are Q are free projections. So this coaction is a coaction of CQG generated by these two free projections on the force set. And since these projections are free, this CQG is actually infinite dimensional. And since S4 plus is the largest quantum group that can coact on a force set, one can have a surjective map from S4 plus to this free algebra, and making S4 plus an infinite dimensional algebra. It's just Rangnaledi theorem. So this is all that we will talk about quantum permutation group. And to the next section we will talk, because this talk is about quantum symmetry in multigraphs. So to understand the quantum picture, we will start what the classical automorphisms of multigraphs are. Give a brief description here. So a multigraph VE, that V stands for the vertex set and E stands for the edge set, consists of a finite vertex set V and a finite edge set V. Everything is finite here. And a source map S, that is a map from the edge set to the vertex set, and a target map T, that is again a map from edge set to the vertex set. And we define this Vs and Vt are the set of all initial vertices in the multigraph V and the set of all final vertices in the multigraph Vt. And given a multigraph, we define a notion of the underlying single-edged graph of a finite multigraph VE. So what is a single-edged graph? A single-edged graph basically a simple graph where loops are allowed. So, so in the context of a single-edged graph, we have a vertex set V, and the edge set can be seen as a subset of V cross V. But we are not using the term simple because we want to incorporate loops in our picture. A loop is an edge with a single endpoint vertex. So an underlying single-edged, yeah?
Why it's called a multigraph and not just a graph? What is multi? definition?
What is?
Why it is called multigraph and not just graph? What is the?
Oh, okay. So I mean, in the previous literatures, when people we used to talk about graphs, so they mostly like by default they mean simple graphs. The notion of quantum symmetry that was introduced by Banica, so he just called it a graph. That is, we have a vertex set V, and the A set is a subset of V cross V. But since we want to generalize these constructions in the context of where there are like multiple edges can be in between two edges, in between two vertices. So that's why we are to distinguish from their construction, we are using the term multigraph. This is also called a quiver actually. So this is actually a finite quiver, one can also say. Okay, so given a multigraph, how this underlying single-edged graph is constructed. So basically, we are like picking up 2 points, and we are taking out all the multiple edges between those 2 points, and we are replacing them with one single edge, and that is the underlying single-edged graph of a multigraph. An automorphism of a multigraph is a pair of bijections, AV and FE. So these are strictly classical picture. I'm not talking anything quantum here. Such that the following conditions hold, that the bijection of the edges and the bijection of the vertices, they are compatible through source and target maps of the multigraph. So the source and target maps, they are the only restrictions that is being imposed on this multigraph. They have to be compatible through that. And this group of automorphisms, the set of all of these automorphisms are the group of automorphisms of the multigraph, and they are denoted as G dot VE. So in this talk, we will try to make non-commutative generalizations of this classical group G dot VE. So the quantum symmetry in single-edged graph. So again, that what I was saying, that in the context of simple graphs, the notion of quantum symmetry is a very well explored object. And for a single-edged graphs, just simple graphs or loops are also allowed. So for a single-edged graph, there are 2 notions of quantum automorphisms that was provided by Banica and Bichon. So first Bichon's notion came, then actually Banica's notion came, but we will describe it in reverse order here for our purpose. And Banica's construction is actually a little more general than Bichon's one. So the starting point is a quantum permutation of the vertex at V, that is a coaction on the algebra CV of a CQG A delta, and it is said to preserve the symmetry of the graph VE in Banica's sense if the following holds. That is, this matrix Q commutes with the adjacency matrix of the graph. So Q equal to AQ, where A is the adjacency matrix of the graph. That is Aij. That is A is a n cross n matrix. With n is the cardinality of the vertex set, and a ijth entry is 1 if there is an edge from I to j, and otherwise it is 0. So if the matrix is symmetric, then our graph is undirected, and if the matrix is not symmetric, then our graph is directed. One can interpret it like that. And this matrix Q is basically the transformation matrix of alpha. So this permutation will preserve the quantum symmetry graph in Banica's case if its transformation matrix basically commutes with the adjacency matrix of the graph. So that is Banica's picture of quantum symmetry. So we will dive a little more into this. We define this map alpha 2, which is again coming from alpha, and it's a map from CV tensor CV to CV tensor CV tensor A, given by this description. Basically, what we are doing is that we are applying alpha on both coordinates, then we are putting a flip between second and third coordinate, and then we are using the multiplication map of the algebra A to make it land in CV tensor A. So what this map does is that quantum permutation of the vertex at alpha preserves the quantum symmetry of VE in Banica's case if and only if this map alpha 2 preserves the function algebra of the edge set inside CV tensor CV. And here C means the function algebra on the edge set, and C is defined to be basically it is seen as a linear subspace of CV tensor CV, that is chi I tensor chi j, where I and j, ij, this pair is an edge. So this is an if and only if condition. And moreover, if this map is a quantum permutation of the edge set E, so in the context of Banica, we have just said that this map has to preserve this subspace. But if this map also is a quantum permutation on the edge set, that is, this map also becomes a coaction on the function algebra on the edge set, then we said that alpha is a coaction on VE in Bichon's sense. So historically, this notion actually came a little different way, and before Banica, then actually Banica generalized Bichon's construction, which actually got very famous in the literature later. So the main objective of this talk is to generalize these two constructions in the context of a multigraph. And the main point is that these constructions are formulated in terms of the adjacency relation of the graph. But in the context of a multigraph, an edge is not uniquely determined by the adjacency relation of the graph. So one just cannot use adjacency relation of the graph to capture all the edge permutations. So we need to go a little different way. And for that purpose, we see this function algebra on the edge set L2E. So now we are writing L2E because we are seeing the function algebra as a Hilbert space with respect to the standard orthonormal basis instead of seeing it as an algebra. So when you will see it as a Hilbert space, we will write L2E. When you will see it as an algebra, we will write CE. So we see L2E as CVS, L2E, CVT bimodule, where VS and VT are the sets of all initial and final vertices. And the left and right multiplication are basically given by, let's say, chi I into chi sigma, where sigma is an edge and I is an element of VS, is basically 1 if I is a source of sigma, and otherwise it is 0. And similarly, the right multiplication is also given via the target map of the multigraph. And there exists, so this dictionary will be very important for the theorems that will come after this. So, and there exists an injective algebra homomorphisms, capital S and capital T. Capital S is a map from this algebra CVS to the operators on the Hilbert space L2E, and capital T is a map from CVT to the operator space on L2E, and they are given by S of chi I equal to summation tau in EI p tau, where p tau is an orthogonal projection onto the one-dimensional subspace generated by this edge tau, and E upper suffix I means the set of all edges that is originating from I. And similarly, the description of T is given, that is T of chi j, where j is a element of Vt equal to summation tau in E lower suffix j, that is the set of all edges that is terminating at j, p tau, and p tau is again is same as this p tau. So what we are doing by this maps S and T, basically we are identifying these function algebras as operators on the Hilbert space L2E. And this identification will be very crucial, that we'll see. But before that, we'll introduce a notion of what a biunitary map on a finite dimensional vector space is. So given a linear map beta, so here we don't have to take CQG here, it's just a sister algebra. Given a linear map beta L2E to L2E tensor array, we say that beta is biunitary if the transformation, if its transformation matrix, use sigma tau in E and its star basically. So this is basically the transformation matrix of the contragradient map of beta, and they both are unitary matrices in MNA. So once we work in this biunitary environment, we are basically are working in UN plus, and UN, the notion of UN plus was also introduced by Wang in another paper named Free Product of Quantum Groups and all. So for a unitary map beta, and we have a sister algebra homomorphism. So if beta is a map on the Hilbert space level, then we have a sister algebra homomorphism at beta, which is a map on the operator space level. That is the set of all operators on the Hilbert space given by this conjugation. That is at beta of T, where T is an operator on L2 equal to beta T tensor 1 beta star. And one can see that why the condition unitary is important here, because let's say if we have T and S2 are two operators, then one can just write beta T tensor 1 beta star and again beta S tensor 1 beta star. And to make it an algebra, for at beta to be an algebra homomorphism, this beta star beta will cancel out since beta is unitary. So this dictionary will be very crucial for the next two theorems that we'll describe now. That is the left and right equivalent co-representations. So this is the first theorem, that let beta be a biunitary co-representation of a CQG A delta. So now we have left the realm of sister algebra. Now we are moving to the realm of CQGs. And that is why our biunitary maps has to be compatible with the co-product of the CQG, and that is why we are taking biunitary co-representation, not just a biunitary map. Then the following are equivalent. That is, at beta preserves this image of S of this functional algebra on the set of all initial vertices, one can simply interpret as that at beta preserves the set of initial vertices of the multigraph VE. And this condition is equivalent to saying that there exists a coaction, that is a quantum permutation of the set of all initial vertices, such that the pair alpha s comma beta respects the left module structure of the bimodule CVS L2E CVT bimodule. That's what we have defined in the previous slide. And we also have a target version of this theorem, which says that again we start with a binary co-representation beta of a CQG A delta. Then the following conditions are equivalent. That is, the at beta bar preserves the set of all target vertices. Here you are using the contragradient map beta bar, not beta. And this is equivalent to saying that there exists a quantum permutation of the set of all target vertices, that is a coaction on this algebra CVT, such that the pair alpha t comma beta respects the right module structure of CVS L2E CVT bimodule. So basically what you are doing here, we are starting with a map on the edge level, and we are trying to capture some permutations on the vertex level. That is exactly opposite of the philosophy what has been followed till now in the context of simple graphs. That Banica and Bichon, they started with a quantum permutation of the vertex set, and they somehow started to adjust. They somehow tried to capture the adjacency relation of the graph, but we are now going exactly to the opposite route, because there can be multiple edges between two vertices. So one can see that these coactions, basically alpha s and alpha t in the previous theorem, they are uniquely determined by beta because of these identities. And here basically q I k in vs, this is and q so there's a small typo here. This will be rjl in vt. So these q's and r's are basically coming from the transformation matrices of alpha s and alpha t, and this u sigma taus are coming from basically the transformation matrix of beta. And one can see that these entries on the right hand side are uniquely determined by the coefficients of the transformation matrix of beta, making alpha s and alpha t uniquely determined by beta. So these coactions are termed as the induced permutation on the sets of initial and final vertices, that is the set of all initial and target vertices of VE. So till now we have only exploited the bimodule structure of the graph, nothing else. But as it turns out that it is not only enough to consider the bimodule structure of the graph, because there does exist non-isomorphic graphs with non-isomorphic automorphism groups, but isomorphic bimodule structure. See, for example, so here we have two single-edged graphs, and one can see that the left-hand side doesn't have any quantum symmetry. So basically, the automorphism group of the left-hand side is nothing but CZ2. But the right-hand side, one can freely permute these 1, 2, and 3, 4. So basically, if we have two projections permuting 1, 2, and 3, 4, we can simply take the free product of them, and one can see that that also describes an action of that free product on this graph. So this thing does have a genuine quantum symmetry, where so the right one does have a genuine quantum symmetry, where the left one doesn't have any quantum symmetry at all. But they have isomorphic bimodal structure. So in light of these discussions, we have found that it is important to consider the behaviors of the induced permutations on the common region, that is VS intersection VT. So basically we have found that they have to be equal. There is no other way out. And now we come to the main definition of the talk. That is, we introduce the notions of quantum symmetry in a finite multigraph. And again, we start with a binary co-representation of a CQG A delta, and it is said to preserve the quantum symmetry of VE in Banica's sense if the following conditions hold. That is, at beta preserves the set of all initial vertices, at beta bar preserves the set of all final vertices, and the induced permutations that we just found in the previous slide, the induced permutations have to agree on the common region, that is C of VS intersection VT. And the fourth is that beta has to preserve this very special vector, where xi0 is tau in E chi tau. So it's basically another way of saying that beta has to be an unital map. And furthermore, if beta is a quantum permutation of the edge set E, that is, this map beta is basically a coaction on the algebra CE, then we say that beta preserves the quantum symmetry of VE in Bichon's sense. So we have used Banica's and Bichon's name here, though this definition was introduced by us, because this generalizes Banica's and Bichon's notions of quantum symmetry in the context of simple graphs to multigraphs. Moving on. So now we'll explore some properties of actually of this definition. So just some waters. Yeah, so let C1 V and C big V be the categories consist of CQGs coacting on this multigraph VE, preserving its quantum symmetries in Banica's and Bichon's sense respectively. And so now one can show that the universal objects in these categories actually exist, and they are denoted by Q1 V and Q big V. That's the name that is mentioned in the title. And the CQG, the Q big V, is basically can be termed as a quantum automorphism group of the multigraph VE in Bichon's sense, whereas the CQG Q1 V will be referred to as universal quantum group associated to V. So why Q1 V is not termed as a quantum automorphism group? Because as it turns out that Q1 V actually captures more than automorphisms. I mean, there are if we abelianize Q1 V, we won't get just G of V. We won't get something bigger than G of V. So to remedy the situation and make a true generalization of Banica's notions of quantum symmetry in the context of multigraph, we somehow needs to shorten the category C1 VE by imposing some extra restriction. And that is exactly where this subcategory C V comes into picture. By imposing an extra restriction, namely the condition restricted orthogonality. So this is also the main definition of our paper, that a bi-unitary co-representation beta of a CQG A delta is said to preserve the quantum symmetry of VE in our sense. Now we are actually using the author's sense here. In our sense, if beta is a coaction on VE in Banica's sense, and it further satisfies the following, because we are shortening the category C1 VE. That is this map add beta ijkl. So what is this map add beta ijkl? So first we fix two pair of vertices ij and kl such that eij, that is at least one edge from I to j, and at least there is one edge from k to l. So that's what it's meant by eij not equal to 5 and kl not equal to 5. And what you are doing is that we are considering, let's say, two projections pij and pkl, which orthogonally projects onto the subspace generated by the elements of eij and ekl. And now we are chopping off the map at beta by this on both the domain side and the range side. And we want these chopped up maps at beta ijkl and at beta bar ijkl to preserve the truncated, the chopped up diagonals inside this algebra. So this kind of looks ugly, but I admit. But once we see this condition in terms of the transformation matrix of beta, it will look fairly intuitive. So the let A delta beta, this is an object in CSMV that is say triplet. So beta is the action of this CQG A delta on the multigraph V. The transformation matrix of beta satisfies the following, where U sigma 1 tau star, U sigma 2 tau, and equal to U sigma 1 tau, U sigma 2 tau star equal to 0. Where sigma 1 not equal to sigma 2 in eij and tau not equal, in eij and tau lies in ekl. So notice that if we have a simple graph, then there can be at most one edge from I to j. So this condition, sigma not equal to sigma 2 in eij, becomes redundant. So basically, in the context of, by imposing this extra restriction, we are not actually, in the context of a single-edged graph, we are not imposing something new. This condition only makes sense when we talk about multigraphs. And this happens to remedy our problem. So complete orthogonality, that is, if we don't chop at beta like the way we did, and we just demand that at beta to preserve the whole diagonal in BL2E, and this demand actually essentially leads to Bichon's notions of quantum symmetry in the context of a multigraph. That means that we have given too much restrictions in the category C1V that we have landed on C big VE. And if V is this is exactly what I was talking about, that if V is single-edged, then we have not given any new restriction. That is, this system V is exactly equal to C bar V. So, and by looking at this, one can say that system V is a true generalization of Banica's notions of quantum symmetry in the context of simple graphs. And if V is a multigraph, then system V actually sits between the other two categories that was described before. But the problem is that this chopped off condition doesn't behave well with respect to the co-product of the ambient quantum group, that is Q bar V. And for that reason, it is still not known that whether for an arbitrary multigraph V, whether CSIM V admits a universal object or not. But by existence of an universal object in CSIM V has been proved for a certain class of multigraphs, where this technical condition is satisfied, that the Banica and Bichon category agrees for the underlying weighted single-edged graph. Then we have shown that CSIM V actually admits a universal object. But for an arbitrary multigraph, the existence is still not known. So since we are talking about quantum automorphism groups here, so it is important to look into how the universal object in CBig V, that is a quantum automorphism of a multigraph that we have in our hand, looks like. So in that context, we'll go to the notion of uniform multigraph. So a uniform multigraph is of degree n, is basically a multigraph where basically there are either n number of edges from I to j, or there are 0 edges. And that is exactly what is meant by this condition. And for a uniform multigraph, an edge can be written as a triplet like this. So where I is a source of tau and j is a source of tau, and r is varying from 1 to n. So what we have done basically we have fixed two vertices, and we have numbered all the edges in between two vertices, 1, 2, 3, 4, n. And why uniform multigraphs are important? Because any non-uniform multigraph can be written as union of uniform multigraphs, where so it can be also termed as uniform components of a multigraph. And to study the symmetry of V, it is enough to study the symmetry of its uniform components, which can be patched up on the common regions. So here basically I have explicitly written what En is. So En is basically tau in and edge in is such that kinarity of this set is n, and Vn can be described by this description. So yeah, so it's not that important here right now. So maybe I'll move on because I don't have much time. So description of cubic VE, that is the quantum automorphism group of the multigraph VE for uniform multigraphs. So we start with a uniform multigraph of degree n, and let VE bar be the underlying simple graph, that is the single-edged graph. We consider the sister algebra, that is, so Sn plus is basically a quantum permutation group on the n elements, and we are taking the m times free product of this sister algebra, where m is the kinarity of E bar. And notice that the elements of E bar are basically the pair of vertices. It's E bar is a subset of V cross V. So this inclusion map of this free product can be indexed by pair of vertices. That's exactly what we'll see now. That there is a natural coaction of cubic V on this free algebra, which is given by this description, where this QIK QJs, they are coming from the generator set of cubic V. And notice that V bar is a single-edged graph. So to describe cubic V, we don't need the machinery we have developed just now. We can just talk about it like we used to do before in the context of single-edged graph. And these canonical generators of cubic V bar actually comes from the transformation matrix of the map on the vertex level. And these news are basically the inclusion map of the free algebra. And one can show that with respect to this coaction alpha, cubic VE, the quantum automorphism group of the multigraph VE in Bichon says, can be written as a free Reed product formula this. So this notion of free Reed product formula is also a non-commutative generalization of the free Reed product of groups, and it was first described by Bichon in 2004, and it originated as a quantum automorphism group of a disjoint union of graphs. And here actually we have provided another application of that free product concept. And one can notice that why this type of formula only seems to work in the context of Bishop's quantum symmetry, because this map alpha has to be a coaction, and for that thing, the action of cubic V or cubic V bar on the edge level has to be a proper coaction on the algebra CE. And that kind of facility is only available if you work in Bishop's category, not in Banica's category. And that is why this kind of formula is only relevant when we talk about Bishop's category. So next we will talk a coaction of a non-Bishop type. So we have completely described how cubic V looks like, but what is a coaction of a non-Bishop type? So we recall that for a multigraph V, this inclusion of categories that I have just explained 3 slides before, and we have described the universal object in C big V. We have said nothing about Sysim V right now. We have just defined this category, and we have said some things about Siban V. So what is the guarantee that the condition, the chopped off condition, the restricted orthogonality that we have put in Sysim V is not too strict that Sysim V actually coincides with C big V. So for that thing, we need to produce something in Sysim V which doesn't lie in C big V. So by a non-Bishop type coaction on a multigraph VE, we mean an object of Sysim V which doesn't lie in C big V. And that is actually the second part of our work, quantum symmetry in multigraphs part 2. That paper is totally concerned about constructing this explicit coaction on a multigraph VE. So let us consider the universal sister algebra cubic V generated by the symbols QKSIR. So now basically we are, when you are writing it like this, Ki in V R is equal to 1 to n, we are actually working with a uniform multigraph of degree n. And we are trying to formulate a coaction of non-Bishop type on a uniform multigraph. So, and we want these symbols to satisfy the following relations. That is, the matrix satisfy these coefficients of the matrix satisfy quantum permutation relation. So basically, the starting point of this construction is a quantum permutation of the set V cross Xn, and we are now, and we'll be imposing some extra conditions on what it means to like the concept of the symmetry of the graph. And the second condition is basically says that this permutation of the V cross Xn has to preserve the subalgebra CV tensor 1 inside CV tensor Cxn. It somehow means that it has to preserve the set of all vertices of the multigraph VE. And the other two conditions, they basically mean that this permutation of V cross Xn has to preserve the edge set of the multigraph. So notice that this approach to the symmetry of the multigraph is completely different than what you are talking about. And since we are looking at it differently, but it is kind of surprising that we ended up on the we ended up producing an object in our category. So this universal sister algebra QVE, one can show that there exists a coproduct on QVE. That is, this condition doesn't behave badly with respect to the coproduct of the ambient quantum group. And one can show that this is in fact, this sister algebra is in fact a CQG. And not only that, there exists an action. So now, of course, so now I'm in action here. So there exists an action of this thing on the multigraph V, which is given by this map. So this is again an edge level map, because to produce an action in CSIM BE, we need to produce a map on the edge level, not on the vertex level. And we have just independently defined this algebra, and we have just giving a map on the edge level by this prescription. And it turns out that this thing doesn't always need to lie in C big V. And yes, we have provided instances of that in our paper, but it is always an object of Sysim V. So it's an action of non-Bishop type. So now we'll just shortly go through an example, then maybe we'll stop. So, and in this example, we will use the Reed product formula that we have mentioned before. So here, like, we have a multigraph. There are 4 vertices and 8 edges, and they are all directed because in your multigraph there are source and target maps. And the right-hand graph is basically the underlying single-edged graph of this multigraph, where we have plucked out all the multiple edges and we have replaced them with one single edge. And one can see the classical automorphism group of the multigraph VE is given by the Reed product formula, that is G odd VE. So basically, classically, it also given by the Reed product formula, where Z4 is basically the automorphism group of this underlying single-edged graph, and it acts on 4 copies of S2 indexed by the elements of E bar. So the generators of S2, they basically permute these two edges, these edges between two fixed vertices. And what the action of Z4 is that Z4 is transporting these permutations from one pair of vertices to another pair of vertices. And that's how the automorphisms are produced. And as you have seen, that similar formula also holds in the quantum case. The quantum automorphism group cubic V is given by the free Reed product formula, this. And here one important thing to note is that the underlying single-edged graph doesn't have a quantum symmetry. It is the Z4. So Banica's category of quantum symmetry in the context of the single-edged underlying single-edged graph and Bichon's category in the context of the underlying single-edged graph, they actually agree, because there is nothing quantum here. And that is why CSIM-V, our category, also admits the universal object, and that is nothing but this object cubic V. So cubic V can be termed as just the quantum automorphism group of the graph, and it is given by the Reed product formula this, where C of Z4 coacts on the free product of 4 copies of S2. So this is why I use the term co here, because Z4 acts and CZ4 coacts on the free products of S2 plus, given by the similar formula as in the classical case. So the like the linear prescription that you have given before, that is like similar to the classical case, but instead of acting on the like Cartesian product of S2, CZ4 is coacting on the free product of this algebra CS2s. And passing on to this free product actually enables us to demonstrate genuine quantum symmetry in the system. So basically, Wang's idea of quantum symmetry was inherently originated from these free product things. So, and how to describe this quantum symmetry in the system? That let us consider a coaction of the CQG S2 plus. So this is we are taking a 4 times free product of this algebras S2 plus, which is nothing but CS2, 2-dimensional algebras, on the function algebra of the edge set CE, because we need to give a map on the edge level to produce a coaction on the multigraph by the following transformation matrices. So here, what we have done is basically we have fixed all the vertices and we are just permuting these edges, and we are like taken free product of these permutations. That is what is meant by this transformation matrix. And PQRS are canonical generators of this algebra. And this is actually a Bichon type coaction, not a non-Bichon type coaction. And the non-Bichon type coaction that we talked about, if we like analyze those type of coactions in this context, one can see that P will be forced to equal to Q will be forced to equal to R equal to S. So this will be nothing but S2. Anyway, so Bichon's picture actually captures this free product thing very nicely. So now we'll like talk about some applications and further questions. So in the context of quantum symmetry, we have shown that all the actions of all the mentioned categories live to the level of graph system algebras, and graph system algebras are interesting object to study because they are mostly infinite dimensional algebras, whereas the function algebra related to graphs are not. So they are like truly non-commutative thing associated with a graph. And in particular, the action of Q1 VE on the associated graph system algebra of the multigraph V actually is a type of action that doesn't type from the automorphism of the multigraph. This is just an interesting fact to observe. But so about this, though we have like produced some non-trivial objects in this category system V, we still don't know whether like when this category will admit a universal object, and when there is a quantum automorphism group in this category and when it is not. So in that context, finding more examples and non-examples where the category admit universal objects and further investigations into them actually is a necessary thing to follow. So I mean, there can be like more projects related to this after this. And the last question that I'm currently working on is various notions of quantum isomorphisms between simple graphs arise from deep connections between the theory of quantum groups and quantum information theory. So basically, these quantum isomorphisms they basically arise as analyzing quantum strategies on non-local games on the simple graphs and all. But there is no notion of a graph isomorphism game in the context of a multigraph. Or there is also no notion of a quantum isomorphism in the context of a multigraph. And these notions of quantum isomorphisms in the context of single-digit graphs, they somehow implicitly they always use Banica's idea of this adjacency matrix commutation things. So in that context, since now we have given a generalization of the Banica's action in the context of a multigraph, so extension of these ideas in the context of multigraphs and explore whether they have any implications in quantum information theory is actually a good direction to live. I think, do I have any more slides or? Oh no, so yeah, so I think I finished before time. So there are some references, and these are paper, Quantum Symmetry in Multigraphs Part 1, which basically deals with the general picture of the quantum symmetry. And this Part 2 is already published, and this basically gives a much simpler way of looking at it by producing an object in SSMV. And actually, I'd like to mention that the object that we have developed in during the, as a non-BISO type action, they're actually heavily dependent on how we label those edges one to one. Like a certain type of those type of actions, they actually fail to live in the same category if we change the labeling. So yeah, so they are like a much specialized thing, but they are also easy to compute. So yeah, I think that will be all. Thank you for listening.
Thank you,
everybody. Yeah, so any questions, I'd be happy to answer.
Can you hear me?
Hello?
Can you go to slide number 9?
Slide number 9, okay. Just wait. Yeah.
Yeah, so
this is the slide that you want.
Yeah, so the space L2E, you are saying that this is a CVA CVT bimodule. So do you mean this is a Hilbert bimodule? Means is there a CVT value inner product on L2E?
Okay. Yeah, you can give a CVT valued inner product on L2E. So basically, what you are talking, the language of sister correspondences, right? So actually, yeah. So in my PhD thesis, so I haven't mentioned it here. So one can see that if you like go through the language of sister correspondences, you will exactly end up on the same construction that has been done here. So yeah, I mean, you can see it like that. That is another way of looking at it. But what happens is that like this. So here the algebras are different, VS and VT, but as the computations turn out, that you can just work with CV, L2E CV bimodule. Instead of VS, you can take the whole vertex algebra. But if you initially start with the whole vertex algebra, then you won't get this map S and T to be injective. So you won't get the identification set of all initial vertices as operators on the Hilbert space L2. That you won't get.
Okay.
So yeah.
I have question. I have some question.
Yeah, sure. Please go ahead.
Yeah, so I have several questions. So usually, when you consider symmetry of classical symmetry of of a finite object, a finite graph, usually what you get is a finite group. Usually when you consider quantum symmetry, what you get is some infinite dimensional thing. So we are missing something. Why? So quantum should be infinite dimensional. There is no way to make quantum symmetry of finite objects, which are always finite dimensional or something like that. Well,
yeah, in the context of finite spaces, the classical symmetry, the algebra of the automorphism of a finite space will be always a finite dimensional object. That is because the classical permutation group itself is a finite dimensional, and any group that can act on a finite structure, that is something like a finite set with some relations, it will always have to be a subgroup of Sn. So the functional algebras are always finite dimensional, but in the context of quantum symmetry that actually I have explained here when you are explaining quantum permutation group, it is not the case. Like for n greater than or equal to 4, S4 plus is actually way larger than its classical counterpart S4. So
have you heard about some alternative quantum symmetry which keep finite dimensionality or no? You never heard about it?
Okay, so can you please, second, because the audio got cut a little bit and I could not follow.
I mean,
sorry.
have you heard about another approach for quantum symmetry which keep finite dimensionality for finite objects?
Okay.
Have you heard about that or not?
So no, actually I haven't. So what do you mean by dimension here? I think there can be a different meaning of dimension there.
Yeah, the dimension over the complex field, if you like. But it's,
so what I'm talking about, the dimension here is just a complex dimension. I mean, just the vector space dimension, nothing more than that. But yeah, there are like different description of dimensions. So I think in that, actually I haven't heard about it. So maybe I would be interested to learn about it in the future. I mean, that like looks nice and all. Yeah.
And my last question. Okay, so this approach was initiated by Wang. So you make a compact quantum group from so the notion of quantum symmetry. So what you make is a compact quantum group. So it's more or less off algebra. So the question is, can we make some generalization of this approach, not to make off algebra, but to make some more general tensor category or something like that? Because you are always restricted to off algebra in some sense. But you are more general quantum symmetry with tensor category. So it could be nice to have a process of quantum symmetry which generate tensor category, which are not necessarily coming from off algebra.
Yeah, sure. I mean, that would be actually a very interesting approach. Basically, those kind of things were kind of in my head when I was writing my thesis. But I mean, so my thesis was on a completely from an algebraic viewpoint, and from that point of view, actually, it was easier to compute algebras than easier to compute tensor categories. So that is why, I mean, we needed to produce some examples such that this free products and stuff. So that's why we took the algebraic viewpoint. But yeah, I mean, that thing that you are talking that I'm getting, it's a very interesting approach to go actually. I mean, to take in this context. But I mean, I personally know what this tensor categories language of the compact quantum group, sorry, not a compact, of a quantum group is, but I have never worked in it. So I am not that proficient in it. Maybe I will maybe try to see this thing in that language, and that will kind of like help me out. And yeah, so basically what you have done is that the single agent, in the context of simple graph, the Banica and Bichon of quantum symmetry and all, they exploited the quantum permutation relations, basically. But we have exploited the bi-unitary relations. That is mean we are working in the algebra UN plus. So, and that was also something that was introduced by Wang. So we are simply exploiting something else that was introduced by Wang. So we are like Banica and we all are working in the same kind of this big algebraic quantum groups. So yeah.
Okay.
But yeah, I mean.
Yeah.
Please.
No. I guess it would be interesting to have this kind of generalization. I am done with my question.
For the quantum permutation group, I asked that, can we find some quotient such that the quotient is finite dimensional and it is CQG? Okay.
Yeah, the finite dimensional, you can, so you can simply make the algebra commutative. Like you can quotient with the commutator, and commutator of a non-commutative algebra, that is like, that is also a CQG and acting on the space. And why do you land in that? You will land on CG or V, and that was the whole philosophy of the thing, that if we abelianize the algebra, that we need to get back the function algebra of the automorphism group of the multigraph, and that is itself a finite dimensional algebra, though it is commutative. But yeah, it is a finite dimensional algebra, actually.
So you can consider quotient, or you can consider sub-object, quantum subgroup. Even if it is infinite dimensional in general, you can find some quantum subgroup which are finite dimensional also. So, can you hear me?
Yeah. Actually, the voice is kind of getting cut, so I'm trying to like, yeah. Can you please repeat?
Yeah.
So he asked about the quotient, which may be finite dimensional, but you can also consider quantum subgroup or sub-object, which may be.
Yeah, because if something is non-commutative, like the infinite dimensionality is kind of an inherent property of a non-commutative algebra. Like if like two elements P and Q, they don't commute, then PQ, 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 P, PQ, 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 P, they are all like linearly independent stuff and all.
I see. So it's free, you mean?
So that is why the infinite dimensionality comes very naturally in the non-commutative picture than the finite dimensionality. And that is exactly what I said, that when you said that maybe you are talking about a different description of dimension altogether. It's not just the complex dimension, because complex dimension, infinite complex dimension is an inherent property of a non-commutative algebra.
Sure. Yeah, you have some other notion of dimension. You have Frobenius per dimension, something like that.
Yeah.
Okay. Okay, so let's take you again. Thank you very much.
The pleasure is mine to present. So yeah, thank you.